Hi guys, this is another video for reaction feasibility. So this video we are going to discuss about feasibility and spontaneity again, um, related to Gibbs free energy. Okay, so what is that feasibility and spontaneity? I guess I've explained it in the first video itself. So it is clearly states that spontaneity or feasibility is a reaction that takes place without any inputs of energy. And how can we actually measure it? We can measure it using total entropy change, right? So the total entropy change, total, right, is equals to the entropy change of the surrounding plus with the entropy change of the system. Okay, and then the formula for calculating total entropy of surroundings, is actually negative enthalpy change over the temperature plus with the entropy change of the system, which is product minus reactant for the system, all right, for particular reactions. And then these can be equivalent to, if we multiply everything with the temperature, so I'm going to get temperature multiplied with entropy change total equals to negative enthalpy change. All right, and we get temperature against system. All right, if we multiply temperature for the whole thing, you will get these systems. And then if we multiply it with -1, then we will get a final equations. Negative temperature entropy total equals to positive enthalpy change plus with temperature multiplied with, this is negative system. Got that? So this is the final equations. Now, why am I doing that? From total entropy change, we derive it into this form, because when negative temperature multiplied with total entropy, this terms is actually equivalent to another new name. They call it as Gibbs free energy. Okay, and the symbol for it is Gibbs free energy change, G. And why do we need this? If we know that the total entropy change, it's sufficient to tell us that whether a reaction is feasible or not based on whether it's a positive or negative values. Let me revise a bit. When total entropy is a positive values, it means that the reaction is feasible or spontaneous. When total entropy change is equals to a negative values, then the reaction is non-spontaneous or not feasible. All right. Now I'm changing it into Gibbs free energy terms because the whole reaction, whether it's feasible or not, we should actually look at the temperature range. All right. Like I mentioned in the first video, certain reaction is not feasible. Yes, the total entropy change is negative, but then the total entropy change will change from negative to positive when the temperature change. So since temperature is the main factor, is one of the factors that affecting the overall system, then we should include temperature in the equations. Hence, at the end, we get a new term called Gibbs free energy. So this is how the derivations work. So when you multiply with negative temperature, you get this Gibbs free energy, and Gibbs free energy is equivalent to enthalpy change minus temperature multiplied with entropy system. Okay, so I can rewrite it as Gibbs free energy change equivalent to enthalpy change minus temperature multiplied with entropy system. So this is the overall equations for us to calculate Gibbs free energy. Now this Gibbs free energy will have slightly different unit. Gibbs free energy is same as enthalpy change. We put it as kilojoules per mole. So when you apply any calculation using these equations, the enthalpy change automatically is in kilojoules per mole, right? But then, knowing that the entropy system that we calculate just now using product minus reactant, they are actually in joule per Kelvin per mole, right? So then you have to convert this into kilojoules per mole per Kelvin. So you change the joules into kilojoules before you actually substitute into these equations, and then we calculate the total Gibbs free energy or the Gibbs free energy change. Alright, so this is how we actually calculate the Gibbs free energy. And looking at this Gibbs free energy, we can see from this pictures, from these graphical presentations, when your Gibbs free is less than 0, or if it is a negative values, which is this, they call it as exergonic reactions, not exothermic. In this case, it's exergonic, and the reaction is spontaneous. It is opposite of what total entropy change states. So in this case, when the Gibbs free energy is more than 0, which is a positive values, then we call that as endergonic reactions, and the reaction is a non-spontaneous reactions. Got that? So it is totally opposite of total entropy. Just now we learned that when entropy, total entropy is positive, means it's spontaneous without considering temperature. Okay, temperature was not in the picture yet. And then now that we include temperature, a range of temperature over a range of temperature, then we are considering Gibbs free energy. So the whole things will be different. When Gibbs free is positive, then the reaction is not spontaneous. When Gibbs free is negative, then the reaction is considered as a spontaneous reaction. Okay, hope you don't get confused here. This will be the graph, and then look at that. This is important. When a reaction is at equilibrium, then the Gibbs free energy is equivalent to 0. Because just now we were talking about positive and negative value. What if it is exactly Gibbs free energy change equals to 0? That means the reaction is in equilibrium, reversible reactions. They can form the products, they can form the reactants, but not complete reactions in either directions. So they are not completely not fissile, they are not completely fissile, because they will not get 100% products. They are still in a reversible state. So this is Gibbs free energy. Alright, then we look at these tables. Now these tables summarize everything. When you have the formula of Gibbs free energy equals to enthalpy change minus temperature entropy. This is systems, always remember, even though sometimes they don't put it as specific as that. So based on these equations, we can calculate what is your Gibbs free. It's either positive or negative overall, right? And then it all depends on the enthalpy change as well as the temperature with the entropy change. So they can be positive or negative. The temperature can be low or high. Now this table actually summarizes under certain conditions, we can for sure that the entropy change is always negative or is always positive. Okay, so this table is for us to make a quick deductions on whether the Gibbs free is positive or negative without doing the calculations in a way, right? So look at the first example here. If the reaction is endothermic, meaning that the enthalpy change is more than 0, makes sense? And if the value of entropy here is referring to system always, unless they put surrounding. So if the entropy is negative, then the Gibbs free energy is always positive, regardless of the temperature. I repeat, if it is an endothermic reactions, the enthalpy change is positive. When the entropy is negative, then the Gibbs free is always positive. Hence, the reaction is never spontaneous, regardless of temperature. Low or high, how great is the temperature range, the reaction is always non-spontaneous. Okay, this is the case where you have endothermic reactions and negative entropy. Next is, we look at this first. When you have an exothermic reactions, enthalpy change is negative, entropy is positive, which is opposite like just now. Okay, your entropy is positive, enthalpy is negative. Then your Gibbs free is always negative. Hence, the reaction is always spontaneous regardless of the temperature, whether it's low or high. Okay, even though it's a negative temperature, 0 or yeah, any temperature. right? So this will be the case where when you look at the reactions, when you look at the data given, if the enthalpy change is negative, the entropy is positive, straight away you can tell the Gibbs free, it's always negative, which is always spontaneous. All right, same goes to the endothermic reactions, but then we have another two optional options here. Look at these two. What if you have both positive? Then it's highly dependent on the temperature. It will be positive, non-spontaneous, when you at low temperature. It will be negative, spontaneous at high temperature. So it's highly dependent on temperature when both enthalpy and entropy systems both giving you a positive values. Same goes to when both giving you a negative values. It is again highly dependent on temperature. It is positive overall, never spontaneous at high temperature, spontaneous at low temperature. So only these two, the one in the cross, you have to pay extra attentions when both having the same sign, whether it's positive or negative, then it is highly dependent on the temperature. So this is a table for us. I'm not asking you to memorize it. It's just that it's a quick reference for us whether a Gibbs tree is always positive or always negative, or it actually depends on the temperature. Make sense? So this is how Gibbs free energy works, and I have worked out the derivations for you to get these equations. In exam, no derivations question, of course, but they will give you all the necessary informations, and make sure you know how to substitute in, especially like I mentioned, the unit must be consistent, all in kilojoules, all right? And then you will get the respective Gibbs free. Then you can tell or make a conclusions that, oh yeah, this reaction is a spontaneous reaction, or this reaction is a not non-spontaneous reactions. All right, that's all about it for this video about Gibbs free energy. All right, I'll see you in the next video, the last one, which is Ellingham diagram.